Today, I want to show you the 4 calculator skills on the TI-84 that come up every single year on the AP Calculus exam. If you can do these 4 things confidently, then you're going to be in great shape for both the calculator multiple choice and the calculator free response questions. I'll walk through each skill step by step and then show you how it's used in a real-life AP Calculus exam problem. Be sure to stick around at the end because I'll also share 3 bonus calculator tips that will help you save time and avoid easy mistakes. Let's dive in. The first skill I want to talk about is being able to evaluate a derivative. If you are given a function rule, you need to be able to give a numerical approximation of its derivative at a particular x value. Let's see how we're going to do that on our calculator. You're going to hit Math to bring up the Math menu, and then you're going to hit 8. You can see that says N-deriv, deriv for derivative. Now, when I do this on my app that you can see on screen, it looks like this. On your calculator, it will probably look a little more like this. Okay, you have some boxes to fill in. If you fill those in and hit enter, it will give you the approximation of the value of the derivative. So, as a quick example, let's say we want to take the derivative of x squared plus x and evaluate that at x equals 1. Now, we can check this by hand, right? The derivative of x squared plus x is just 2x plus 1. When I plug in x equals 1 to that derivative, I should get 3. And indeed, that is what the calculator gives me. You can see on your calculator, maybe, there's more boxes to fill in. Let's just check we get the same thing. So d by dx, I'm picking the variable I want to use. I'm taking the derivative of x squared plus x and evaluating at x equals 1. When I do that, I again get 3 as our answer. So how might this come up in an actual AP exam question? Well, in the 2023 AB exam in FRQ number 1, you're given a rule for a function g. It's this cosine looking thing, and you're asked to find g prime of 140. You're asked to evaluate the derivative of this function, find a value. We can type this into our calculator, no problem. Let's see how we're going to do that. So again, I'm going to hit Math to pull up the Math menu, hit 8 for my numerical derivative. You can use whatever letter you want for your variable on your physical calculator. Generally, I recommend sticking with X because it has that nice, easy button for you to press. If you want to stick with T, as in this problem, you could, I guess, but you'd have to be messing with the alpha button. It just doesn't seem worth it to me. So let's stick with X. So what is my expression? Well, it is the variable divided by 500 times cosine of the variable divided by 120. I'm squaring that quantity, closing out the cosine, and then I'm evaluating at the variable being 140. So when I hit enter here, I get this numerical approximation, which to 3 decimal places is negative 0.005. That's our answer. There's nothing more to it. Of course, as we might know, the flip side of differentiation, finding derivatives, is integrating, finding integrals. And that is the second skill we need to be able to do. We need to be able to input a definite integral onto our calculator and get a numerical approximation of the answer. How are we going to do this? Well, we're going to again pull up the Math menu, and this time we hit 9 for function integral, fn int. It again pulls up, very helpfully, the skeleton of a definite integral. You can see what it looks like on the physical calculator again as well, with one more box to fill in for the variable. But let's check how this works. So if I do the integral from 0 up to 1 of an integral that I know how to deal with, say 2x, that is my variable. Well, an antiderivative for 2x is just x squared. If I evaluate at the end, evaluate the limits and take a difference, I should get 1, right? That's the answer that we're expecting to get here. And indeed, that is what we end up with. Simple, right? Let's see how it might come up in an exam setting. So if we look at the first free response question on the 2019 AB exam, we are given a rule E of t that is modeling the rate at which fish are entering a lake. Okay, we want to know how many fish enter the lake between t equals 0 and t equals 5. Now, I don't want to worry too much about the calculus going on under the hood here, because again, this is a video on calculator skills, but ultimately this is a net change theorem problem. The number of fish entering is the area under the curve of that rate function. The area under the curve, we should be thinking of a definite integral. So for this problem, I just need to compute a definite integral of this rule between t equals 0 and t equals 5. We just saw how to do that using the math 9 fn int property of our calculator. So let's see it. We're going to do math 9. Let's put in my limits of the integral, so it's 0 up to 5. I'm then doing my rule, which is 20 plus 15 sine of pi times my variable, in this case I'm using x again, by 6. So when I enter this, I get this approximation, 153.458. If we're rounding that to the nearest number of whole fish, that would be 153, I guess. So the calculus going on in the problem was maybe a little more involved than the first FRQ that we saw. Maybe this is making us think, oh, I need to brush up on my net change theorem problems. But the actual calculator step was super straightforward. It's math 9, enter the information from your definite integral. Doesn't get much better than that. Okay, our third calculator skill is we need to be able to graph a function in an appropriate window. Let's see how we're going to do this. So we're going to enter the function rule by hitting y equals. We then have all these nice rows for y's that I can enter my function to. So if I say y is going to be x squared minus x, and then I hit that top right graph button. Wonderful. We've got this nice graph. I can check this on my physical calculator too, so I do exactly the same steps. I'll hit y equals, I'll enter x squared minus x as my rule, and now if I hit graph, I get that quite pleasing curve being drawn like that. So that's how we graph a function. But I didn't say just graph a function, right? I said graph a function in an appropriate window. And that word appropriate changes depending on the problem, and that can be the rub. That can be what trips you up if you aren't able to see the features of the function you're graphing because your window isn't looking in the right place. So to see what can go wrong there, I want to dive into an exam problem. So if we look at FRQ number 2 from the 2023 AB exam, we're told that a swimmer is swimming with velocity given by this kind of gnarly looking function. And we want to know where the swimmer changes direction between t equals 0 and t equals 90. So my brain's going already when I'm reading this problem, right? When I see velocity, when I see changing direction, I know that change of direction happens when velocity changes sign, either from positive to negative or from negative to positive. The velocity changing sign means I'm traveling in the opposite direction. Okay, well, let's graph this function and see where it changes sign. So let's go back into our y equals. Let's clear out that function. I'll enter my function rule 2.38 e to the power of negative 0.02 times the variable. And then I have my sine function, and it is pi divided by 56 times my variable. Wonderful. And now we just hit graph, right? Oh. Well, okay. This is what we mean when we talk about an appropriate window. You can see that the velocity changes from negative to positive at the origin, okay? But my time started at t equals 0, so I'm not really interested in what is happening beforehand. So I need to figure out what's happening between t equals 0 and t equals 90. This is when we remember I need to graph in an appropriate window, Let's hit the window button. So when I go into the window button, I can control lots of different features of my axes, ultimately. You can see I've got my X min and max, my Y min and max. So if I want my horizontal axis to be focused between 0 and 90, which from the problem I do, I can just enter that as so 0 up to 90. And now when I hit graph, okay, very nice. I can see when that velocity changes direction, okay? It's happening between 50 and 60, when t is between 50 and 60, I guess. I somehow need to find that intersection point, right? And that'll tell me the time at which my swimmer changes direction. But I'm not going to do that right now, because that's actually skill number 4. Being able to find intersections is our last calculator skill, so I want to dive into that as our final separate topic. So, finding intersections. There are 2 different kinds of intersections we might want to find. We'll either want to find an x-intercept, so where our graph crosses the x-axis, or we might want to find the intersection of 2 curves, right? That comes down to solving when 2 functions are equal to each other. So let's treat these one at a time. We're going to do this all graphically. So let's pull up y equals that menu and enter in a function. So let's say I'm going to do x squared minus x again and graph that. Oh, well, I don't really have an appropriate window right now because this is the window left over from my swimmer problem. This can happen to you in the middle of the exam, okay? So this is a great instance to remind ourselves we always need to be graphing in an appropriate window. When you're in this sort of situation and you're not necessarily sure what an appropriate window would look like, I like to hit zoom and then do 6, which gives us a standard box back, which is plus or minus 10 on my axes. This is still perhaps not great. Maybe I want to zoom in a little more. I can hit the zoom button and then 2 to zoom in. If you're doing that on your physical calculator, you would hit zoom 2 and then enter to make the zoom in happen. So how do I find these intersection points? Well, I can read them from the graph, sure, but I can also have the calculator tell me what's going on. So to find an intersection with the x-axis, I'm going to do second trace. You can see that gets me to my calculation menu. And I want to figure out a 0 of a function. Remember, graphically, the x-intercept of a graph corresponds to a 0 of my function. So if I hit 2, I now need to help the calculator out a little bit because there might be more than one x-intercept. So here, it's asking me for a left bound. It's asking me for a right bound. So I'm going to sandwich the intercepts that I'm interested in. And then it finds that x-intercept for me. In this case, it was x equals 1. If I'm doing this on my physical calculator, okay, let me zoom in. So I'm going to hit zoom 2 and then enter. Okay, I've zoomed in a little bit now. That's nice. So now again, I'm going to do second trace to bring up my calculate menu. I'm going to hit 2 for 0, and again, it's asking me for a left and a right bound. So I'm going to pick that same intersection point, left bound, right bound. Okay. But then on your physical calculator, unlike the app that I'm using to show you on the screen, you need to enter a guess. Your guess can be pretty bad, but it's just your best attempt. You're going to hit enter one more time, and then, it finds that x-intercept as before. Wonderful. So that's finding x-intercepts of a single function, a single graph. What if I've got 2 graphs and I want to see where they intersect each other? Well, let's go to y equals and enter a second graph, say ln of x, and then I'll maybe shift that up by 2. If I have that graph, okay. Is this an appropriate window? Well, maybe. It looks like I'm missing an intersection point, right? It looks like they're about to intersect just off screen, so I'm going to again do that same trick as before where I just do zoom 6. It gives me my standard window back, and I can now see both intersection points. So To find an intersection point of two graphs, I need to hit second trace, get back to my calculation menu, and then hit 5 for intersect. Now again, we're looking for a left bound. We're looking to sandwich between. I've sandwiched between and it's found that intersection at x equals 2.24949 and so on. Let's see how this is going to go on our physical calculator. So I'll go to y equals, I'll add that second rule. So it was ln of x plus 2. If I graph, same issue as before, I'm missing the intersection point. So let's do zoom 6. I'll see my two curves appear again. And now I'm going to do second trace to get to my calc menu. I'm going to hit 5. It then asks for what your first curve is. So I'm going to say, okay, yep, that's my first curve. My second curve can be this one. Okay, that's great. And then it wants me to give a guess. So it's going to say, okay, let's navigate the cursor to near the intersection point and just hit enter. And you can see I get the same value. So let's see these skills in a couple of different exam problems. From the 2012 multiple choice problem, number 82, we're asked to find where a function whose derivative we are told a rule for, we're asked to find where f has a local maximum. So let's graph this function. I know a rule for f prime. I don't know a rule for f, but I can certainly graph the derivative. So it is the square root of x to the 4th power plus 1 plus x cubed minus 3x. That's my rule. If I graph it, okay, I've got a pretty decent window here. I can see the features of the graph seemingly well. Now, where f has a local maximum, again, let's not focus on the calculus too much, but that is going to happen where the derivative of f changes from positive, because my function should be increasing, to negative. I want to have a local maximum occurring. So looking at this graph, I can see f prime, which is what I've graphed, has changed from positive to negative at this point a little bit past x equals 0. So let's go second calc. I want to find a 0. Again, I'm going to sandwich the intersection point that I'm interested in, like so, and it gives me x equals 0.350 as the x value of where f has a local maximum. Could do it on our physical calculator again, it would be exactly the same steps. You would just need to make that guess after you've sandwiched the left and right bounds. What about for finding the intersection of two curves? Well, from the 2025 second free response question, we're given that f of x equals x squared minus 2x, and we're told a rule for g prime, not g, but g prime, and we want to find the x value between 0 and 1, where f and g have parallel tangent lines. Okay. Well, parallel tangent lines means the slopes of the tangents are equal. Slopes of the tangents are measured by derivatives. So I want to know what x value between 0 and 1 has f prime being equal to g prime. Well, let's graph f prime and g prime and use our intersect feature. Let's go for it. So we're told that g prime is 1 plus pi cosine of pi x. That's my first rule for the derivative. The second function is f of x. But remember, I want to compare g prime, the derivative, with f prime, the derivative. So if f is x squared minus 2, f prime will just be 2x minus 2. Just taking the derivative of that polynomial. I'm not even going to look at the graph yet, because I know I'm only interested in the interval 0 up to 1, so why don't I go in and change my x min to 0 and my x max to 1. That means when I graph it, I know I'm seeing exactly the right region that I'm interested in. Okay, I've got my two curves. I want to find that intersection point. Second trace to bring up calc. Hit 5 for intersect. And now here I'm doing left bound, right bound. It's giving me that intersection at x equals 0.676. We could do it on our physical calculator. It would just require picking a first curve and a second curve, that sort of thing. Okay, those are our 4 skills that show up every year on the AP Calculus exams. What were they? We need to be able to calculate a derivative value, be able to estimate a definite integral. We need to be able to graph a function in an appropriate window and find intersections, either of a graph with the x-axis or of 2 curves. If you can do those 4 things and you have a solid foundation of the calculus underpinning each problem, you're going to be in really great shape. I promise you some bonus tips. So, first things first, do not think that your calculator needs to be used on every single calculator active problem. If you look through the free response questions that have calculator active, if you look at old multiple choice problems that are calculator active, sometimes you do not need to use your calculator. So don't waste time tapping through your calculator trying to find a way to solve the problem using your calculator when you think you have a way into the problem using your own actual understanding of calculus. Just because you have access to the calculator does not mean you have to use the calculator on every single calculator active problem. Bonus tip number 2, always show setup for your calculations. Your math teachers have probably been saying this to you for years, but this is where the rubber meets the road, because if you look at the scoring guidelines for lots of the FRQ problems, it will say, do not give any points for unsupported work. Okay, I know you're under time pressure on the AP exam. I'm not expecting you to write paragraphs and paragraphs, but write down your thought process that shows why you're doing what you're doing on the calculator. You can look through practice problems, you can look through scoring guidelines to see exactly what is expected. But if you just write down the answer, put a box around it, you might get 1 point from that, you might even get 0 points for that. So leave a trail of breadcrumbs to show your thinking, your reasoning, so that the reader that is grading your exam knows what you were doing, how you were justifying, so they can give you the maximum number of points. My final bonus tip is simply to say, you are smart, your calculator is not, okay? I know a lot of students put so much faith and trust in their calculator, but it's that old saying of rubbish in, rubbish out, okay? If you type in nonsense into your calculator and don't evaluate for yourself if you think it makes sense, and just write it down as your answer, you're missing a chance to maybe catch a mistake, okay? Your calculator is doing its best with the information that you are giving it. If it feeds you an answer that doesn't make sense, say you're expecting a derivative to be positive because you know something is increasing, but you get a negative answer, that probably means you should go and check something. If you get an answer of 10 trillion, right, if our number of fish entering the lake over 5 hours was 10 trillion, that doesn't seem so plausible. So just be thinking, does my answer actually make sense? And that's all I have for you. Thank you for sticking with me. As I've said, these 4 skills are so key to the calculator sections of the AP Calculus exams. So really give them your attention, practice them until they are second nature. If you're still watching, I'll put a link to an FRQ practice playlist right here, calculator focused. And if you want something else to practice, here are the calculator multiple choice questions from the released 2012 exam. Look forward to seeing you next time. Bye.